Welcome to Polynomial Functions and Graphs, Part 2. Notice that we have several polynomial function forms over here on the left. The first one is linear, degree is 1. The second one is the quadratic, degree is 2. Remember, the reason why you know the degrees is because it is the largest exponent. The third one is the cubic with the degree 3, and the fourth one is the quatric with the degree 4. So the largest exponent within the polynomial determines the degree of the polynomial. And here we have graphs of each one. So we have a linear function, straight line, the quadratic, parabola. Then we have a cubic function over here on the bottom left, and then the quartic function. That's what it sometimes looks like. Polynomial functions. If f of x is equal to 3, this is a constant function. You know it because here is your horizontal line at 3. Okay, the degree is 0, and thus the maximum number of zeros, remember zeros, we also call them roots, okay, as well as the x-intercept, okay? So that is what, remember from the last time, x-intercept. So remember from the last time, we learned that zeros, roots, x-intercepts all are the same thing. And notice there are none for a constant function. For polynomial functions, this time this is a linear function. We only have a degree of 1. So the maximum number of zeros is 1. So your linear lines always cross the x-axis once. All right, let's look at this next one, a quadratic function. Please tell me how many degrees it is. That's right, it is 2 degrees, which means the maximum number of zeros you have is, that is correct, 2 zeros. Alrighty, let's look at the cubic function. Okay, the cubic function is degree 3, and our maximum number of zeros is going to be what? That's right, 3. Here is our quartic function, and it is a degree 4, so that means the maximum number of zeros that you can have is, that's right, 4 zeros. All right, let's look at the two graphs. These are cubic polynomials. We're going to look at the two graphs and discuss the questions below. How can you check to see if both the graphs are functions? That's right, the vertical line test. How many x-intercepts does graph A and B have? That's right, they have 3. What is the end behavior for each graph? Now this is a little trickier. So for graph A in blue, notice as x approaches infinity, y approaches infinity, and as x approaches negative infinity, y approaches negative infinity. Because, let me see what happened to my, here it is. So as x approaches negative infinity, y is approaching negative infinity. Let's check out the other one. The other one's just the opposite. As x approaches infinity, the y is approaching negative infinity. And as x approaches negative infinity, y is approaching infinity. Okay, what else do we want to ask about? Which graph do you think has a positive leading coefficient and why? And which graph do you think has a negative leading coefficient and why? So answer the question. That's right. Graph A has a positive leading coefficient. And the reason why is because the parent cubic function rises up from the left. See, it's rising up from the left and continues to rise to the right, which means a positive leading coefficient. While on the other side, on graph B, it has a negative leading coefficient, which means you're looking at a negative x cubed. So it's coming down, okay? And then continuing down because it is a negative x cubed. Think about it. All right, let's take a look at some cubic polynomials. The following chart shows us some properties. So we're going to focus on the roots or the zeros or the x-intercepts. Notice your x-intercepts. There's 3 of them in this case. It's -4, -1, and 2. Notice that in factored form, you take your x-intercepts, put the opposite in with the x, okay? And then you can FOIL it out in order to get your standard form of x cubed plus 3x squared minus 6x minus 8. The sign of the leading coefficient is positive, and then you can see how your end behaviors work. And look at the domain and range, all real numbers, okay? Let's look at the next one. Oops. Look at that. So in this case, notice that again, we have the same roots, but the way that the graph is being drawn is the opposite way. And that's because there is actually a negative in front of our x cubed. Look at that. So all the signs have changed, okay? So we have negative x cubed minus 3x squared plus 6x plus 8. All right, but the roots are the same. Notice that each root only has one set of parentheses. Okay, so the sign of the leading coefficient is negative in this case. Let's look at the patterns for this cubic function. Now we don't have 3 x-intercepts, we only have 2, -3 and 1. But notice in the factored form that your x plus 3 is squared. Now remember, when you have an even multiplicity, then it winds up touching the x-axis but turning there, okay? The sign of the leading coefficient for this is positive. All right, and again, your domain and range for these are all real numbers. All right, let's look at the next one, and that is that we're still looking at the same x-intercepts. You still have x plus 3 squared and x minus 1, but the leading coefficient is negative, so there's a negative in front of your x cubed. All right? All right, one last example for cubic polynomials. Okay, notice now that we're down to one x-intercept. However, notice the flattening along that x-intercept. And that's because we have x minus 2 cubed. So you have a multiplicity of 3. The sign of the leading coefficient is positive. Again, the domain and range is all real numbers. On the red graph, please notice that again, you have a flattening there. The factored form is a negative x minus 2 cubed, so the multiplicity is 3 again, and you have a negative leading coefficient, and your domain and range is all real numbers. Okay? All right, now we're going to look at the quartic polynomials. We're going to look at these two graphs. Can you check to see, how do you check to see if both graphs are functions? That's right, it's the vertical line test. How many x-intercepts do the graphs A and B have? Looks like they've got 4 x-intercepts. What is the end behavior for each graph? All right, so as we look at graph A, notice that as x gets larger, goes to infinity, y is going to infinity. And as x goes to negative infinity, y is also going to infinity. Okay, remember that a quartic is an even function. Okay, if we look at b, notice that as x goes to infinity, our y is going to negative infinity, and then as x goes to negative infinity, the y is still going to negative infinity. So the y's for your even functions are always in the same direction, no matter if your x is going to infinity or negative infinity. Okay? Which graph do you think has a positive leading coefficient and which graph do you think has a negative leading coefficient? That's right, graph A has a positive leading coefficient. Why? Because even polynomials on the end behavior of the lines are the same direction, and if you're positive, then that means they're pointing up. While graph B is negative, and so even polynomials means that the end behavior, the lines are pointing down. Let's look at some examples, okay? So here we have, and this circle here has two of the x-intercepts in them. I couldn't get it small enough. Notice again the factored form there was going to be x minus 3, x minus 1, x plus 1, x plus 2 that represent your x-intercepts. Notice that on this one, both sides are going up, so that means that your leading coefficient is positive. And the domain and range are all real numbers for the domain. The range, though, notice how it starts here and then it goes up. So you have to be careful with these. Your cubics are all real numbers for both domain and range. That's not so for your even polynomials, okay? Let's look at this next one. Again, the x-intercepts are the same, but in the factored form, we have a negative in front of our x to the fourth, which then means that our leading coefficient is negative, so we're looking at the y values going downward. And so here would start your range, and then your range would continue down. Okay, so it's all y values, 12.95 less than or equal for y. All right, let's take a look at this pattern here. Okay, notice how we are down to 3 x-intercepts. So when we do it in factored form, notice that at 4, where the x-intercept is 4, the graph comes down, touches 4, and then turns. So it's a turning point. It does not cross. Again, both these sides are pointing up. So we know that we have a leading coefficient that's positive. The y range starts at negative 16.95 and then goes up. Okay, let's look at this. Okay, we have 3 x-intercepts, and in the factored form, notice that the 4, where it turns, has 2, a multiplicity of 2. Okay, this is a negative. Notice how both sides go down. So we know we have a negative leading coefficient because there is a negative in front of our factored form. Also notice that the range is going to start at 16.95 and go down. All right, let's take a look at this set. We are down to 2 x-intercepts. And so in our factored form, notice how we have a multiplicity of 3 here for the x minus 2. So notice the flattening. It really flattens out. Again, we have two arms pointing up, so the leading coefficient is positive. Notice that for the y, the range starts at negative 8.54 and goes up. Okay, on this one, again, the same. two x-intercepts, the factored form. The only thing is we do have a negative in front here. Notice that we have a negative leading coefficient because the arms are going down. Notice that your range starts at 8.54 and goes down from there. All right, here's our last example of a quartic. This time, notice that we just have one x-intercept. Notice the real flattening of the line here as we look at this. And we have an x minus 3 to the fourth, so you have a multiplicity of 4. So this almost looks like a quadratic form. Notice that you have a leading coefficient that is positive. Also notice on this example that our range starts at 0 and then goes up. On the bottom one here, again, we have only one x-intercept, but again, it has a multiplicity of 4. Our leading coefficient is negative because both our arms are going down. Oops. Both our arms are going down. And notice that our range starts at 0 and then goes down. So it is y less than or equal to 0. And those are our examples for a cubic and a quartic polynomial functions. Thank you for your participation. The end.